So in the last video here for chapter 10, we're going to look at a couple different types of reactions. First, epoxide ring openings, and then we're going to look at some reducing agents. So here for epoxide ring openings, they function very similarly to what we've seen already with carbonyls opening up. Okay, because we have, right, an oxygen species, right, and we have these carbons which we know are electrophilic, right? To kind of remind ourselves here, right, epoxides, right, these three-membered oxygen rings, right, are strained, and so the carbons are electrophilic, right? So an example we have here, right, we have a methyl group on one side, phenyl group on the other, right? Remember, phenyl groups are these aromatic rings, right? And so, because this oxygen, right, three-membered ring is really strained, right, it doesn't like being in this conformation. So these carbon bonds here are actually sort of weakened because of that. So there are these partial positive charges on these carbons. And if we remember from our Orgo 1 discussions, we know that carbons like to have positive charges on them when they have, right, more things connected to them or something with resonance. Right, so we see each of these carbons are secondary, right? They're both attached to two other carbons, but this carbon here, right, has something that can do resonance, right, which helps to stabilize, right, a carbocation intermediate. So in truth, the majority of the partial positive charge is on this carbon, right? So this is the weakest bond here. So in terms of our reaction, right, what does that mean? So if we're looking at our, if we're looking at the mechanism for this, we see we have drawn MGBR incorrectly, right? Should be like this. But, right, we're looking at this, and so we should be thinking, okay, this, this nucleophilic carbon here will attack the more partially positive carbon, right? So let's show this in a mechanism here. So it's going to come around and attack the backside of that oxygen-carbon bond, right, just like an SN2 reaction, to get us to this intermediate here. Right, these wedges and dashes have not changed, but now we have this CH3 down below. Right, and in that final step, we just have quenching occurring, and we'll just go ahead and show that mechanism as well, to get us to our final, right, alcohol product. Right, just another reaction here to show how to draw or form an alcohol. Okay, so hopefully that makes sense. Okay, so for the last set of reaction we're going to look at, this is something called reduction. So we're turning, I mean, again, right, we're going from a ketone or a carbonyl to an alcohol, but this time we're not doing it with a Grignard reagent. We're doing it with a hydride, just a hydrogen. And so how does that occur? So we're getting this H- species here, which is a hydrogen with a lone pair on it. Right, attacking a carbonyl, it opens up, just like we've seen before with those ketones, and we have this final step where we quench the reaction to some sort of acid, like this, to get to our final alcohol. And so we can do this in two different ways. We can use two different reagents here. Sodium borohydride, which is a weak reducing agent, and this can turn aldehydes or ketones into alcohols, or lithium aluminum hydride, which is a strong reducing agent. And it can do essentially any carbonyls here, right? Aldehydes, ketones, carboxylic acids. It can do acid chlorides as well. Okay? So how does this occur, right? How does this hydrogen get formed here? So in short, what it really happens is we have, right, for a weak reducing agent, it'll be the same for the strong reducing agent. We have this borohydrate here, and what happens is the, right, hydrogen here wants to fall off of the boron, right, this group 3 element, to generate H-, Okay, so the electrons on the boron hydrogen bond here have ended up on the hydrogen, which is our strong reducing agent, or reducing agent period. And so in both cases here, for the sodium borohydride and lithium aluminum hydride, we're forming either way H minus. There's no difference there. But with sodium borohydride, the H minus falls off slower essentially, and here it falls off faster. Right? That's the only difference. Okay. So let's look at a couple examples of what's happening here. So we have two examples that have two carbonyls on them now, right? Two of these carbon double bonded oxygens. And so what we have occurring in step number 1 is a selective reduction. So only one carbonyl is going to get reduced, right? Because we have, right, our weak, right, our mild reducing agent. And remember, this is only going to go after ketones and aldehydes, not esters. So we'll not go after this ester here, but it will go after this ketone. Right, so we're forming our source of H minus from, right, sodium borohydride, and it's going to come in and attack our ketone here. Then we have our final step where we, right, quench the reaction, and so we end up with this alcohol here, and our ester remains untouched. And I'm showing the hydrogen here just for clarity, right? This hydrogen has attached itself, right, from the top or bottom of this trigonal planar carbon to get our alcohol. All right. And for this next step here, right, we have a strong reducing agent. So nothing is safe here, and everything is going to get totally reduced down to its alcohol component. And so for the ketone up above, right, that's pretty easy to think about what that looks like, right? We're just having that H minus come in and attack. And so we have our alcohol here, okay? And I'll show the hydrogen again for clarity. And I guess in truth, I should be saying, right, excess. It's kind of implied, but I'll be clear here, right? So we have as much H minus as we need to get to our final product. And down below, right, we have this acid chloride, right? And like we've seen with those carbonyl reactions where we can go from an acid chloride, right? We can do, right, a substitution to get to another carbonyl, but then we can do a final addition to get to an alcohol. Right, with the ketone, we just did an addition to get to an alcohol, but here, right, we can have, right, our chlorine, right, leave as our leaving group, and then we do a final hydride addition, right, to go all the way down to just a regular alcohol, okay? So do the mechanism on your own for this and see if you can come up with this following product, right? Show H minus attacking each of these carbonyls as much as we need to, and see if you can come up with this final product. And in class, we'll look at some more examples of these reduction reactions, okay? And one other thing we'll cover is a retrosynthesis problem. So we're going to start looking at more of these, okay? And so we'll cover this in class where we try to figure out how we can make this material here, starting from starting materials with no more than 6 carbons.